Hello, everyone. We are very happy to have Amit Sever with us today. Amit will talk about line operators in Chern-Simons-Matter theories and bosonization in three dimensions. Okay, so Amit, please start.
First, thank you very much for the invitation to speak. This is really a pleasure. And please stop me at any minute with as more questions as possible. I prepared for 1 hour, but I don't mind as long as we can go. Let me start by introducing my collaborators. So first, this is Barak Gabay, who is a PhD student at Harvard. And this is Deliang Zong, who is a postdoc at Tel-Aviv University. They are really wonderful collaborators, and I want to present mainly their work today. So this work is based on a short paper that we summarize our work so far, and two long papers that are will be coming out soon. One more focused on the perturbative side and one on the non-perturbative bootstrap. So let me start with the motivation, and I focused the motivation on bosonization in three dimensions, even though this was not our initial or main motivation, which I'll come back to it at the end. So let me start with the short motivation. Not working? Okay. So Chern-Simons theory possesses a well-established non-perturbative level rank duality. It's something that is well understood for pure Chern-Simons theory. But once we couple it to matter in the fundamental representations, this duality is expected to extend into a duality between the Chern-Simons theory coupled to bosons and Chern-Simons theory coupled to fermions. Now, why expected? Because this is a non-perturbative duality, and therefore very hard to prove. And by expected, I mean that now we have a very extensive evidence, especially at large n, for this duality. And the evidence comes from the study of correlation function of local operators, the spectrum of monopoles or baryon operators in the theory, thermal free energies, the S matrices, and sometimes relating non-supersymmetric dualities, well-established supersymmetric one. And here I listed many people that work on it, and especially some in the audience today. I hear some noise in the background. Maybe someone.
You know, it may be me. I'm sorry. I will disconnect and so on. Join again. Okay. Sorry.
Just try to mute, maybe. Good. Yes. Much better. So the first evidence for the fact that if you couple matter to Chern-Simons theory, it's interpolate between bosonic and fermionic statistics, comes from the original famous paper of Witten itself. And I want to explain why. So even in pure Chern-Simons, the only observables are Wilson loops. So consider, for example, a closed Wilson loop here. It turned out that in order, the noise is back, in order to define such an operator in the quantum theory and preserve the topological nature of Chern-Simons theory, you have to introduce what is called framing regulator. Framing regularization is like a small vector here along the loop that tell you what you do when 2 points collide. So here it's this small vector, and turn out that the expectation value of this unknot Wilson loop takes the following form. So first, this is the form of this Wilson loop in what's called the planar limit, which is the only limit I will consider today. So I'll consider SUN or UN gauge group at level K, and the large N limit is defined by taking the level or the rank of the gauge group to infinity, while keeping lambda, which is the ratio between the rank and the level, to be fixed. So this ratio range between -1 and 1 depends on the sign of K, if it's positive or negative. The weak coupling limit is where lambda goes to 0, and the strong coupling limit is where lambda goes to 1 or -1, again, depending on the sign of K. Now, in this planar limit, the expectation value of such unknown Wilson loop take this function of the coupling lambda. What I want to focus on is this phase prefactor here. So a phase that is e to the I pi lambda times f, where f is called the self-linking number. is the number of time the framing vector wind around the loop as we go around. So for example, in this picture, it winds once. So here f equal to 1. Okay. Now suppose we take Chern-Simons theory and now couple it to matter in the fundamental representation. So once we couple it to a matter in fundamental representation, we can have such a framed Wilson line ending on a fundamental matter, which is described by the ball here. And now you would naively, intuitively expect that if you rotate this particle around itself, exactly this phase factor will now, you will have to rotate it with the framing vector, and you will pick a phase that starts from 0 at lambda equal to 0 and become e to the I pi when you complete the full rotation when lambda equal to 1, which is the maximal coupling. And this is why this framing dependence will interpolate between fermions or bosons while coupled to matter. Okay? So this is the intuitive reason we expected to be so, and this is something that we will prove explicitly in the planar limit. Okay, so let me be a bit more concrete of what are we going to study. So we're going to take Chern-Simons theory, which is a famous action in 3 dimensions at level k, and couple it to matter made of fundamental bosons or fundamental fermions in the fundamental representation. Now, these are called the quasi-boson or quasi-fermion theory. For the boson, you have to tune some coupling, which is called lambda 6, to sit at the conformal point. So you only sit at the conformal fixed point of these theories. Now, on any side of the duality, there are 2 theories. One is the one described by this action, and the one is the double trace deformation of this theory with respect to what's called J naught square, where J naught is the biscalar or bifermion operator. Okay. And again, one has to go to the other description, to other theory, one has to deform, for example, the bosonic theory by this double trace J0 square, and then flow to the fixed point. Now, what we are going to study, what I think are the most fundamental operators in such a gauge theory coupled to fundamental, which are line operators ending on the fundamental fields, stretching between fundamental and anti-fundamental. And I'll call these mesonic line operators. So let me, before we start, talk a bit about large n counting. What happens when you take n to be large and fix the tooth coupling to be fixed? So it turns out that the matter only contributes at order 1 over n to the expectation value of closed Wilson loop. To the linear order, they are taking the same form as they are at Chern-Simons theory. However, they contributed order 1, of course, to the expectation value of these mesonic line operators. Okay. The double trace deformation, they take you between the 2 descriptions in the two theories, 2 conformal field theories in the bosonic or fermionic description, only contributed 1 over n squared to the expectation value of closed Wilson loop, or the 1 over n to the expectation value of this mesonic line operator. So it's only entered at the next order in 1 over n. However, it contributed order 1 to the correlation function between these mesonic line operators, and this is something I'll come to back at the very end. So in the rest of the talk, we are going to focus on the expectation value of these mesonic line operators.
Sorry, what is the double trace operator in those AC boson and AC fermion?
So the double trace,
yeah. So I don't see any double trace.
It's J0 square. J0 is like a trace, but you take a fundamental and multiply it by anti-fundamental and make a color singlet. So this is what we call like a trace when you have fundamental matter.
Okay.
And the double trace is taking the square of this J0 and adding it to the action and let the theory flow to the IR, at least in the bosonic description.
Okay.
Okay. So at the free theory, the boson is dimension 1/2. So this is dimension 1, you take its square, it's a relevant deformation of the bosonic theory, which generates a flow to a new fixed point. Okay. However, as long as we are only focusing on the expectation value of these bosonic line operators, they are blind to this flow. It only enters for the correlation function between them. So they don't distinct between the two fixed points at lead node.
Amit, suppose we were considering a Wilson line along, let's say, the x-axis, and we were working in the gauge AX equals 0. Then in this case, this would be the same as the propagator in the singlet channel. Right? Is this right? Right. So this would be, because AX would, the Wilson line would be psi bar connected by an AX. If AX was 0, then this would just be, so it's some sort of gauge invariantization of the propagator between a fermion and an antifermion. Is this reasonable?
You will think about it, but the point is that the fermion or the boson itself at the endpoint would acquire both anomalous dimension and anomalous spin. Okay? By itself is not a good operator. So this setup, not in that gauge, but this setup is exactly what we'll use to compute it. But if you consider any smooth line, if you focus close to the end, it looks like exactly the setup you mentioned.
Okay.
As long as it's smooth, close to the endpoint, it looks straight, and this is what we will use actually to compute it.
Okay, yeah, I was wondering the following. In our very old paper, which 3 or 4 of the authors are here, we computed exactly the propagator of 2 fermions in some light cone gauge. And I was wondering whether that was that's some sort of special case of this Wilson line.
If you pick the line to be null, I guess.
Yeah, something like that. Right.
Yes, but there is a bit some subtleties with this static light gauge. That, for example, if you consider a circular Wilson loop, right, and you pick a light cone gauge, and you put it in the plane of plus minus, you would naively say that it's equal to 1. Right? Because all the diagrams in light cone gauge will be identically 0. So sometimes it's a bit dangerous to do that. In the way we will use it, it will not.
Okay.
It turns out it will not. So let me, before we go into a bit of details, let me summarize the main results. So the first step that we did is forget about the endpoints, is to classify the conformal line operators. If you consider a generic line operators like a Wilson line, it may experience an RG flow on the line. So the first step we did is to classify what can be the fixed point of such RG flows. So in the rest of the talk, I only focused on this fixed point on the conformal line operators. After classifying the conformal line operators, we classify the operators that you can place on the line and the operators that the lines can end on. And we did it at finite coupling. Both, I'll go into a bit more details. Next, wanted to understand what is the dependence on the shape of the line. In pure Chern-Simons theory, the line operators are topological, the Wilson line. But once you couple it to a matter, they are no longer topological, and we want to understand the dependence on the shape. It turned out that in Chern-Simons theory, this line operator satisfy a sort of a first-order loop equation. When you do a small deformation of the line, it turned out that this is equal to a factorized product of such 2 lines operators. Next, we took the spectrum.
So just to understand, so evolution by what? Like what kind of evolution?
Evolution in the shape. This is what we mean.
I see.
We take the line and we deform it smoothly.
And then it can always be written like this. Any smooth deformation.
Yes. As long as it's smooth, it can be written like that.
Okay.
And then, okay, the main part of the work, which shall only come shortly at the end, was the line bootstrap, what we call. It turned out that this evolution equation, together with the spectrum of boundary operators, and that's it basically, we show that it's sufficient to determine the expectation value of this line operator.
So just to make sure I understand. It is regarding what Siraj was asking. So if I understand correctly, what Siraj was saying, that you commented that it is related to the 2-point function in some light cone or something. That's what you commented, right? In the
Shiraz think.
What I was saying was that if we in our old calculations we worked out exactly the propagator and the light cone gauge.
Yes, yes.
So if in the light cone gauge A is 0 along the light cone directions, so if the points were also separated along the light cone direction, you might imagine that this propagator becomes exactly Amit's Wilson line. I was wondering whether that was correct. And Amit saying there may be a subtlety.
Maybe a subtlety. And in that language, Siraj, would there be an interpretation of this deformation?
It would be hard for us to make this deformation because we didn't include any of the gauge field. So our line would have to be along the null direction, so as not to get contribution from the gauge field. So any deformation would take us away from this Wilson.
Okay.
Let me add to it. It's a bit technical. I didn't want to go there, but of course, the first step in this computation is to compute the exact propagator, like Shiraz, you did in your work. But we have to introduce a regulator and pick a regularization scheme. It was crucial to pick a convenient regularization scheme, which entered the exact propagator, crucially. But okay, I will try to avoid such details.
But may I say something actually?
Yes.
Amit. Yeah, so I mean, in our original paper, what we did is we fixed the light cone gauge a la at Hooft and just derived the Schwinger-Dyson equations for these mesonic operators. And of course, I mean, we had to use a certain type of regulator to,
if I remember correctly,
but that's what
computed
we did, right?
You computed the correlation function of local operators. Well, the diagram in light cone gauge satisfied.
We recast the entire theory in terms of Wilson lines in the light cone gauge, and you can use the light cone gauge to do that. And we then derived the Schwinger-Dyson equations. Of course, there is no motion because the gauge field is set to 0 on the light cone, which is rigorously true. But these are Schwinger-Dyson equations. So in some sense, the gauge invariant information that anybody calculates would be the same.
Of course. We work also in light cone gauge. I can jump to say, this was just preview of the result. I can go a bit more details of how we did the computations, but I feel that this is a bit too early.
Okay.
So please stop me a bit later.
Okay.
So importantly, we showed that the conformal line operators in the bosonic and the fermionic theory satisfy the same evolution equation, and as the spectra of boundary operator related by the Levin-Reich duality, which map the 't Hooft coupling in the bosonic theory to the 't Hooft coupling in the fermionic theory, plus or minus the sign of the level. Okay? So this in particular map the limit where one of them goes to 0 to the strong coupling limit of the other, where it goes to 1 or minus 1, corresponding to the sign of K. So yes. I could not hear you. Can you repeat, please?
What do you mean by the boundary operators? Are they the operators living on the line?
No, the operators that the line can end on, represented by this dot.
Okay.
Next slide, I will go to details, more details about them. Okay. But the bottom line is that these two together, therefore, infer that the bosonic and the fermionic theory have the same expectation values of these line operators for any smooth shape. Up. Okay. In particular, to the first non-trivial thing you would like to compute, if you could try to compute the dependence on the shape, is what is called the 2-point function of the displacement operator. To try to displace the line in an orthogonal direction by a small amount, this is amount to inserting what is called the displacement operator. And here I put two of these on a straight line, one at xt and then one at xs. And normalized by the same expectation value of a straight Wilson line, mesonic line operators, to remove any normalization dependence. Now, this ratio is equal to the conformal cost ratio associated with these 4 points, the endpoint on the line and the 2 insertions point, to some power. Here delta is the conformal dimension of the boundary operator. Times 1 over x to the 4, the displacement operator always has dimension 2. So this is just by dimensional analysis. And the non-trivial part of this 2-point function is the number that stands here. And we computed it directly from the bootstrap and also by resumming explicitly all order perturbation theory. The same function also controls the 2-point function of the displacement operator on a closed circular Wilson loop, if you normalize it properly, and it's equal to this non-trivial function of the dimension of this boundary operator. Okay? This is one of the boundary operator with minimal dimension, and it's dependent on lambda, depends on which line operator we are considering and whether you are using the bosonic or the fermionic description. But this formula is general and applied to all of them. It basically follows from the form of the evolution equation.
Just a quick question.
Yes.
Is it correct that the shape dependence goes away in the lambda going to 0 limit?
Yes, of course.
Okay.
Because then you go back to pure Chern-Simons,
Great.
where the dependence is topological.
Great. Okay. Thank you.
Okay. So then it becomes just a free propagator. Okay. So for the plane of the talk, I'll start by describing the bosonic theory, and we go describe the fermionic theory, and as time will allow, I'll talk a bit about the bootstrap at the very end. And without loss of generality, I will assume that the level in the bosonic theory is positive, and therefore the Hooft coupling in the bosonic theory runs between 0 and 1, while in the fermionic theory it is negative, runs between -1 and 0. Another option is related to that by parity. And I'll try just to explain the main ideas that led to all the results, but I would not have time to go into details. Depends how much you ask. So let's start with line operators in the bosonic theory. So it turned out that if you study just the most natural line operator to study is just a Wilson line. But it turned out that in the bosonic theory, just a Wilson line and then as a non-zero beta function for the adjoint biscalar. So adjoint biscalar, I mean they're taking here fundamental, anti-fundamental, but they don't contract their color indices. They are like forming together an operator in the adjoint that we put on the line. So the scalar is dimension, the free scalar is dimension 1/2. If we take 2 of these, this is operator in the free dimension 1. So naively, we can worry that it will have a non-trivial beta function, and indeed, it has a non-zero beta function. So we studied this RG flow to all loops, and we found what are the conformal fixed points. And the conformal fixed points, so here is a Wilson line, it's described by some path and some framing vector. It has this condensation, it's non-zero coefficient for the adjoint biscalar. And the coefficient is lambda over n, 2 pi lambda over n, with a coefficient alpha that is equal to 1 or -1. So there are 2 fixed points, one with the coefficient is positive, and one with the coefficient is negative, equal to 1 or -1. And that's it. And you can describe also the RG flow between them. The one with alpha equal to 1, when the coefficient here is positive, is a stable fixed point on the line. And the one with alpha equal to -1 is an unstable fixed point. We can generate a flow to the alpha equal to 1 or to what we call an almost trivial Wilson line, which may become more clear what it is at the end. Okay. There are also other conformal line operators that are less fundamental than this one that involve adding degrees of freedom on the line. I will not have time to describe them unless you ask.
Sorry, Amit, lambda
Yes.
by n is k, right, or kappa? No. It's 1 by
yes.
1 by kappa. Yeah, lambda is n by kappa, right?
Right.
Okay, so
Right.
so if you cancel the n,
So-
this is 2 pi by kappa. It's a very
Yes,
nice
this is 2
number.
pi.
Yeah. Is there
Right,
a
right.
physical interpretation for getting this nice number? You know, 2 pi by e to the power I, 2 pi by kappa appears in the Q deformation of all formulae in Weissenbino-Witten theory. I was wondering whether there was you could have sort of expected this number.
I expected to be order 1 number over K, over kappa. But the fact that it's equal exactly to plus or minus 2 pi, this is the result of a computation.
Thank you.
It will connect to everything I will say before. It will connect directly to the form, to the spectrum, or to the form of the evolution equation. So I can comment on it there later. But the way we started, we just call it undetermined coefficient, and there is some perturbation theory, and so that there are 2 fixed.
Flow on the line, what do you mean exactly? What happens under that flow?
Just a normal RG flow, but now on the line. So the coefficient here will change. So in other words, if you do perturbation theory, you will get logarithmic divergences on the line when they generate a non-trivial beta function for this coefficient.
So the RG flow, the coefficient changes. That's all that happens, is it?
Yes, that's all that happened. This is the only, in the bosonic theory, this is the only relevant operator, if you are starting from the 3 point, that you can add on the line. So this is the only one that potentially could have some non-trivial RG flow. All the other have higher dimension. Yes.
Okay. What's the dependence of alpha on the cutoff?
Alpha does not depend on the cutoff.
I mean, what kind of dependence does it
have? Oh, you mean along the flow?
Yes.
This is, of course, scheme dependent.
Okay.
So now we can take this line operator and let it end on a fundamental or anti-fundamental. I'll call fundamental the right boundary operator and the anti-fundamental the left boundary operator. We can also add operators now in the adjoint on the line, but in the planar limit, they're all factorized into fundamental, anti-fundamental. So once we classify all the boundary operators, we automatically get also classification of all the operators that can leave all the line, because they are direct product of right and left operators. Now, it turns out that these boundary operators are uniquely classified by 2 quantum numbers. One is the conformal dimension, and the other is the transverse spin for rotation around the line. For example, if we are starting at 3 level, and we look on the right boundary on the fundamental, we have the scalar. We can act on it with light cone derivative in the transverse plane to the line, and in that way increase or decrease its 3-level spin. This is S here. And we can act on it also with longitudinal derivatives. Here I place the line along the x3 direction. So dx3 is the derivative along the direction of the line. So at 3 level, this is a classification of all the boundary operators that you can place on the line. Their dimension is, of course, 1/2 for the scalar and the total number of derivatives, whether they are longitudinal or null derivatives.
And this is the large end result. You could receive corrections at finite end?
No, this is 3 level. This is not. Okay. This is just 3 level. What you do maybe. Now, of course, at the quantum level, both the spin and the dimension will get quantum correction. So this is what we are up to compute. Okay. Now, a straight Wilson line, which is always the shape of a smoothly Wilson line near the endpoint, preserve an SL2 subgroup of the conformal group times U1 for rotation in the transverse plane. So it turns out that all these operators with n equal to 0 with no longitudinal derivatives are SL2 primaries. Okay. And the rest are just descendants. Okay. So it's enough to consider the one with n equal to 0, the rest follow for free. They automatically would have the same spin and dimension shifted by 1. So let me jump to the result. Now that this curly S is the full quantum transverse spin, now that it's on the right, it gets anomalous spin, which is minus lambda over 2, while on the left, it gets anomalous spin, which is plus lambda over 2. Which, if you remember, it's exactly the frame independent that was there in pure Chern-Simons theory. This contribution comes purely from the Chern-Simons dynamics. Now the dimension cannot get also anomalous dimension, which is related to the spin by this nice formula. In other words, it's always exactly plus or minus lambda over 2. This relation here, yes.
Difference between SL and SR, curly SL and curly. What is the reason for
this is one is the start point of the line, and one is the end point of the line. Okay.
Yeah. So I mean, there should be a reflection symmetry or something which tells you that
there is no reflection symmetry because the theory break parity. So when you reflect, you have to flip the sign of K. You flip the sign of K, you flip the sign of lambda.
I mean, if you flip the Wilson line about its center, then what happens?
Then you interchange the fundamental with the anti-fundamental. Okay, so
I see. Okay.
The right go to the left. They are not the same unless you flip the sign of K. Okay. In other words, consider a straight Wilson line. It has a rotation symmetry around it. So the spin in order to have a non-zero expectation value, the spin on the right must be equal to minus the spin of the left. And to get this, if you started with such a Wilson line 3 level, the loop correction, if they give you an anomalous spin, it will be opposite on the left and the right. Otherwise, we would not contribute to the expectation value.
Okay.
In other words, the spin is translated by the line from the right to the left and preserved along the line. It's another way of saying the same.
I have a very elementary question, if you don't mind.
Yes.
You know, you defined what is the framed Wilson loop for a closed loop. But did I miss your definition of a framed Wilson line somewhere?
So when I framed an open Wilson line, the one that ends on fundamental, I use exactly the same. Okay?
I see. So that
I'll come back to answer your question. It's one of the equations that when we say what is the form of the expectation value, how it depends on the framing vector, this will appear.
Okay. All right. Thank you.
Maybe just to comment here, this delay. Yes, sure.
Sorry, but just to continue Spenta's question, is the framing vector required to take a specific value at the ends?
No.
So that's an integration variable. It can do whatever it wants at the ends.
It can do whatever it wants at the end, and if you rotate it, you acquire a phase factor.
Okay, thank you. So your thing is labeled by the values of the framing vector at the ends in particular.
Yes.
In addition to topological. Yeah, okay.
Right. Exactly. Just jumping a bit ahead from my slide. I tried to go a bit slower. One comment about yes.
Maybe you will say, but I mean, why is there a nice relation between delta and S? So if it is
yes.
All the dependence to S. So
great question. This is exactly what I wanted to comment on. This originally came out as a coincidence, but when we started to say it could not be a coincidence, it turned out that all the operators I described here would have not exactly the same relation, but a similar one. One can lift them to a locally supersymmetric Wilson line in the n equal to 2 Chern-Simons-Matter theory. Now, suppose you consider one of these supersymmetric Wilson line in the n equal to 2 generalization of what I'm talking about. And say you place only scalars at the endpoint. Turn out that, so first, these turn out to be BPS operators on the part of supersymmetry that is preserved by the line. And this is nothing but their BPS condition. The transverse spin acts like an R symmetry in this reduced supersymmetry on the line. And it turns out that in the planar limit, the fermion, for example, decouple if you just put the scalar at the end. So the expectation value of such a line operator in the n equal to 2 theory and in the bosonic theory will be just the same. Okay, so we can trace this relation back to the BPS condition on a locally supersymmetric Wilson line in the n equal to 2 theory.
Okay, thank you.
Yes.
Just one quick clarification. So this delta tells you how suppose I had a straight Wilson line. Delta tells you how the expectation value of the Wilson line changes under scaling the length of that Wilson line. Is this right?
Yes. Yes.
Okay. Yeah. So
I can jump there. There is a formula.
No, it's fine. Yeah.
Yes. Yeah. So the line itself is no dimension. It's a conformal fixed point. Now only the dimension is localized at the endpoint. Okay. Of course, started at 1/2 in the free theory, but it gets loop corrections. Now, operators that are so, for example, we can get what we call before the conformal descendants by taking path derivatives in the third direction. These are longitudinal derivatives, or we can increase or decrease the spin by taking null derivatives. Okay. So if you think all in all, we are just 4 towers of operators, and all the rest are dictated. All the rest are dictated by these 4 operators by taking path derivatives. Okay. We can start on the left with just a scalar, fundamental scalar, and then we can act with the longitudinal derivative. This is the first number here, going to the conformal descendants on the line, or we can act on it with plus derivatives, generate 1 tower of operators, all have the same anomalous dimension, and their conformal dimensions just differ by 1. Or we can have the operator on the left, we have 1 negative null derivative. This operator has the opposite anomalous dimension than this one. And we have a full tower of operator on top of it, which are obtained by taking path derivative in the minus null direction. And the same on the right. Okay. So it's, in other words, it's enough to compute the dimension of the spectrum of these 4 operators, and all the rest follow from path derivatives. So we did everything explicitly independent of that. So this is what I was saying, that the spectrum was derived first by an explicit all-loop computation. To give a little more details, we in most cases we defined what is called a line integrand, which in perturbation theory it amounts to doing all the loop integrals in the bulk, but not doing the integrals on the line. So, for example, at L loops, you can have up to L integration point along the line. And then we showed that these objects satisfy a very nice recursion relation that you can solve explicitly. Once you do that, you get the anomalous dimension, not only the anomalous dimension, but also the wave function renormalization factor, which in general is scheme dependent, but you can compute some combination of it, such as the 2-point function of the displacement operator that I'll come back to it soon, which are scheme independent. Okay, the relation between the dimension and the spin follow from supersymmetry, this is what I said before. And now you see that this indeed confirms the expectation that if you start from a boson, which is spin 0 for rotation around itself, we go to spin 1/2 at the maximal coupling, which is lambda equal to 1. So indeed, yes.
So why can you neglect the loop corrections on the line itself? I mean, you said that you're taking only.
We generally do not neglect them. The first step was exactly to account for them and flow to the fixed point on the line. So this anomalous dimension here comes exactly because of the interaction with the line, and the loop corrections on the line contribute crucially to it.
Okay. And
for example, at leading order, you would have just a free propagator. Next to leading order, you can have a gluon exchange between the line and the propagator. And this gluon get close to the endpoint, it gives you the 1 loop anomalous dimension. Both it and the scalar are bilinear.
And what did you say about?
Let me be maybe a bit even more detailed. We start by exactly this computation. We naively stretch just a naive Wilson line and let it add on two scalars and try to compute it at one loop. And at one loop, you can write a nice formula for any smooth shape, and there are no divergences, just finite. But then you go to two loops, and the two loops you find suddenly a log square divergence. And this was very puzzling. How can you find a log square divergences without a log F1 loop? Only then we realized that they're actually non-zero beta functions for the scalar bilinear. And once you include it with a coefficient 1 or -1 at 3 level, you find that this log square is exactly the exponentiation of the one loop log that come from the biscalar in the exponent. So at one loop, you would put one biscalar and integrate it, and this will generate a single log.
Okay, just I mean, if you just go ahead, it will be made more clear, I guess.
Okay. But again, this by itself is not the gauge invariant operator. Adding the Wilson line is crucial for all the computation. And because of this anomalous spin, we see here explicitly that indeed we interplay between boson and fermions as functions of coupling. We can now ask what is the spectrum of operators on the line. Okay. Remember, on a straight line, we have a one-dimensional conformal theory. And you can ask what is the operator with minimal dimension that can live on the line. But because operators on the line factorize into right and left, into fundamental times anti-fundamental operators, the operator with minimal dimension on the line is just given by the sum of the operator with minimal dimension on the right plus the operator with minimal dimension on the left. If you look here, it's equal to 1 plus lambda, meaning that this is an irrelevant deformation of the line if you try to add it. And this is why the operator we are considering here with alpha equal to 1 is a stable fixed point. It does not have any marginal or irrelevant deformation on the line. So this is the formula that I think Shiraz was referring to before. What to expect to the form of the expectation value.
Just one question about the previous point. Can you go back?
Yes.
So here to compute the dimension of the biscalar, you simply added them as if they were the boundary point of the left guy and the boundary point of the right guy, right? Because of large.
Yes.
Do that.
With larger.
You observe that it is stable. Okay.
With larger, it just factorized. You add it and compute the expectation value, just have the expectation value of the right times the expectation value of the left. And the dimension just add.
Yes, thank
you. Which is so to say that the single Wilson line splits into two Wilson lines.
Yes, yes. This is exactly the what call it the evolution equation I alluded before. We are coming back to it now. Okay. Well, to talk about. So what do we expect? What the form of the expectation value of such a mesonic line operator should look like? So here we have the factor of x right minus x left to the power 1 plus lambda, which is 2 delta. This is just capture the conformal dimension. It depends on the conformal dimension, the right and the left. Here we have the right and the left values of the framing vector to the power lambda over 2. This is coupled the anomalous spin at the right and the left. If you rotate them, they acquire a phase, which is captured by with P0. So this is just by basically dimension and charge analysis. And what remains here is a non-trivial conformal invariant function of the smooth path that you would like to understand. Okay. And to understand what this function is, this is where the evolution equation comes about. Okay. Sorry. So suppose we start with the straight Wilson line. Yes.
Sorry to interrupt, Amit. In the case of the quasi-fermionic theory, there's no analog of this phi bar phi on the line. Is that right?
Why not?
Because I thought that in that case,
if you put a fermion, anti-fermion, it's not it will be irrelevant deformation on the line, but this is an operator that you can place on the line. At 3 level, it takes dimension 2, and you can combine it to spin 1, which is exactly what you require for the displacement operator.
I see. The fact that it's dimension 2 is in one dimension doesn't make it irrelevant.
It is crucial. It is dimension 2. And I'll come to it exact next. What is non-trivial, that it remains of dimension 2 also will include quantum corrections.
Okay,
so let me go a bit slower. So suppose we start with some smooth path and do a small deformation of it. This is the small P here.
Yeah.
So to linear order in V, what we are doing is integrating an operator on the line that is called the displacement operator. You see, just by definition, this operator must have dimension 2 to account for the dimension of this V and to the measure on the line, and spin 1, which is the orthogonal direction in which they deform 2. Okay. Now, what is written here, it always has dimension 2 in transverse spin 1, depending on the direction of V here. Now, in our case, if you look on the spectrum, there is a unique such operator in the plus and in the minus direction that has this property that has dimension 2 and spin 1. And it's made of exactly this, not exactly, it's made of, we took chiral. It's different if we do the deformation in the plus or in the minus direction. If we do the deformation in the minus direction, the spin here is carried on the left, on the right side of the operator, but this O left. If you do the deformation in the plus direction, it carries on the OY. Okay. At 3 level, this is the scalar times a derivative, null derivative of the conjugate scalar. And this is the other way around. Okay. Now note that these two operators, both of them get both anomalous dimension and anomalous spin. But this anomalous part exactly cancel out in this combination. They have opposite anomalous dimension and opposite anomalous spin. So this combination always have exactly dimension 2 and spin 1. In other words, if you just started from a straight Wilson line, the existence of this operator with this spectrum, exact spectrum, can give you an alternative definition of the operator on an arbitrary smooth line. Another way of deriving this form of the displacement operator is just to derive the Schwinger-Dyson equation for a small deformation of the line. If you do a deformation of the line, from the gauge field, you get the field strength. And from the biscalar, you get an additional combination, which is what is responsible for making this operator look chiral as it is, different from deformation in the plus and in the minus direction.
So this is why you were saying that the deformation is equivalent to separating the two lines and inserting operators in those intermediate points?
Exactly. So now if we do this deformation and we place these operators here, you see that it's factorized into a product of two such mesonic line operators.
Sorry, Amit, how do you know what linear combination of these operators is this displacement operator?
So 2 ways. One way is you brute force compute. You do deformation of the line, you use the equation of motion, and you see what you get. This is a bit naive because this is the standard, the way people derive the loop equation for also Wilson lines in 4D. It is naive because it's formal manipulation without regularization. And so I would not trust it by itself. But it gives the correct result. Another way is to look on the spectrum and to look for an operator which is dimension 2 or spin, transverse spin plus or minus 1. And there is a unique such operator.
Okay.
At any value of the coupling. So what you can use it as a definition of the displaced operator.
Yeah, okay. Yes.
Maybe one related comment, in 4D we used to a loop equation which is second order. You act with the loop Laplacian and get 0 up to contact term from self-crossing. Here, because the Chern-Simons action, the equation of motion, instead of df equal to 0, is f equal to 0. And this is why the analog loop equation is first order instead of second order. Okay. It's much more nice, I think. Of course, we get also the standard contributions from self-crossing, but here I assume that the line do not self-cross.
Amit, I have a small question, but
yes.
Since there are matter fields actually at distinct points, so the Gauss law would be field strength equal to matter fields where they are located actually. So
exactly, this is this equation. If you're in pure Chern-Simons, you get it's independent of the shape. So if you do a smooth deformation, just nothing changes, and you get 0 here. The reason we don't get 0 here is because of the coupling to the matter. So instead of f equal to 0, we get f equal phi d phi bar and so on.
Charge density, basically. Yeah.
Yes. Right. But the technical level, f equal f contracted with the line, with the direction of the line, equal to phi d phi bar plus phi bar d phi.
That's right.
But then there is an additional contribution from the scalar condensate in the action, which exactly cancel one and double the other. And this is why this form is chiral. Okay? Here the derivative is only carry on the left with this OR, and here the derivative is only carry on the right with this O left.
Yes. Okay. Thank you.
Sorry, Amit, one question relating to something I asked before. When we, in light cone gauge, when we computed just the propagator of two scalars, at least my memory was that we just found something of dimension 1. Yeah, I mean, we found 1 over mod x to the power 1. I'm trying to understand how that is consistent with your 1 plus lambda in the first equation of this slide. And
because you have to include the interaction with the line, of course. So concretely here, we pick the line, when we did this computation, we pick the line to be in the fair direction and pick a light cone gauge in the space transverse to it.
Okay. But suppose I now take my line and make it light-like. Then I suppose you say that this would just go to 0.
Light-like is not a smooth deformation of this one. Here I'm working only in Euclidean space.
Okay, thank you.
Okay.
And how are the delta C's related on the two sides of the equation? The deform on the left hand side of this diagrammatic equation on the equation at the bottom.
Here.
No, the equation next to it, the last equation. Yes. So,
this one.
Yeah.
Yes.
So delta C on the left hand side is just the deformation, right?
Right.
And on the right hand side, how is the deformation coming in?
This is just a graphic way of this equation here. So on the right hand side, you integrate the displacement operator weighted by the deformation.
I see.
Okay. So this is the linear order deformation. Later at the end, took a bit. We had to go, of course, beyond leading order and beyond linear deformation in order to really fix the expectation. In addition to the evolution equation, called the bulk equation, they also satisfy what called a boundary equation. You can take, for example, the operator on the left, which was the conjugate scalar, with some positive transverse spin, and then act on it with path derivative in the opposite minus direction. Turns out there is no other operator that you can write which has the right dimensional spin other than the operator with two longitudinal derivative and spin that is reduced by 1. So namely, they should be related with some coefficient. This equation at tree level is nothing but the equation of motion for the scalar, box phi equal to 0. Okay? But at the quantum level, it generalizes into such an equation And one thing we did, we were able to fix this coefficient using the evolution equation and the spectrum. Part of the bootstrap, not to find that doesn't get corrected. Basically, get the same value as you get at 3 level, which is -1/2, so this equation become at 3 level, basically box phi equal to 0. So this is what we call the boundary equations. So now let me, so far we talked about the operator with alpha equal to 1, which was the stable fixed point. We now talk about what happened when we flip the sign of this scalar bilinear in the exponent. So when we do that, it turns out that all the dimensions of spins remain the same, except the one which started the life as the scalar and the conjugate scalar. The one that the 3-level spin was 0. What happened to them is that their anomalous dimension flipped sign. Okay? But all the rest remained the same. So again, we have 4 tower of operators, but now on the left, it's either the scalar and the plus derivative of the scalar, while before it was the scalar and the minus derivative of the scalar. And all the rest of the boundary operator are built upon this 4 by taking path derivatives in the plus or minus direction. Okay? So these two have -1 lambda over 2 anomalous dimension, and these two have plus lambda over 2 anomalous dimension.
So you are saying that before RG flow, if you start out with OL01, it becomes OL0 -1. Is that right? After RG flow.
This is not a statement about the RG. If you do the RG flow, the dimension of this guy flip sign.
Yeah, that's what I'm saying.
Yes.
Precisely. Yeah.
Yes. So yeah, I said it opposite. If you do an RG flow, the dimension of this guy flips sign, not this guy. This guy stays the same. This guy is spin, so it's insensitive to the deformation. If you start with a straight line, you put the operator, which is a 3-level scalar. This guy is spin, it will decouple from it. It's only this one that feels it.
So the n flips sign. So since it's the derivative, power of the derivative, correct?
The one with derivatives do not flip sign. The anomalous dimension stays the same. Just the scalar or the conjugate scalar is anomalous dimension before was lambda over 2, and now it becomes minus lambda over 2. Okay. Before, this one was obtained from this one by taking null derivative in the plus direction. Now they are unrelated. Two different operators. Again, the operator with minimal dimension now is again the biscalar, and its dimension is the one from the right plus the minus on the left. Because these two flipped their anomalous dimension, it's now 1 minus lambda. Okay? So this is a relevant deformation on the line, which can generate a flow back to the alpha equal to 1 operator or to an almost trivial line. Okay. Strangely, this operator, its dimension is also related to the spin, but in a slightly different way from what I was describing before. It turns out it also corresponds to a half BPS operator, can be lifted into a half BPS operator in the n equal to 2 theory. But surprisingly, this operator, it looks the same in the n equal to 2, it's just an opposite sign for the scalar in the exponent. But it's also BPS, and it was not considered before. I guess people thought before that it should be equivalent, but because the theory is not parity invariant, these are really two different line operators. And correspondingly, their supersymmetry lift is two different half BPS line operators. So I'm done with the bosonic theory. Now I'll try to describe the dual of this story in the fermionic theory.
Sorry, but so far you've been talking just about the quasi-bosonic theories.
Oh, Yeah, or the one that you obtained by doing the double place deformation, but because the double place deformation only contributed order 1 over n to the expectation value of these operators, they are they are insensitive. They don't feel whether you are using the quasi-boson or the quasi-fermion.
Yeah, sorry, just something that's confusing me. I'm probably very stupid. Suppose I was just in the quasi-fermionic theory, so that at tree level, my operators were psi and psi bar, my fundamental operators. Then this mixing that you had between the Wilson line, this ADL and phi bar phi.
ADL.
The integration of the gauge field along your line, that's you needed to add this alpha times phi bar phi. That was generated.
Yes.
Yes. Is there an analog in the quasi-fermionic theory of that? Looks to me like that operator's dimension 2 and cannot happen.
Great. This is exactly what I'm coming to next.
Okay.
Yes. So if you are studying the fermionic theory, there is no operator, as Chiral said, on the line that will be marginal or relevant. So at recoupling, there is no RG flow, and the standard Wilson line is a good conformal line operator. So exactly, a Wilson line is a good conformal line operator in the fermionic theory. Nothing that we can add to it that would be relevant or marginal. And we repeat.
Couldn't you insert derivatives inside in between the fermionic operators?
They would just increase the dimension. In order to be on the line, to be marginal relevant, we need an operator whose dimension is 1 or less. But the fermion itself is fundamental and already have dimension 1 in the free theory. Okay. So in the free theory, there is nothing we can put on the line close to the free theory. There is something we can put, but we have to generalize degrees of freedom on the line before. I will not go there. So we repeat the resummation of perturbation theory, everything I was describing in the bosonic theory, also for the fermionic theory. And we find that so we obtain a match, exactly the spectrum between the two. And what started his life in the bosonic theory was being the fundamental boson, become this one component of the fermion. While the other component of the fermion is the dual of the plus derivative of this boson, of this scalar. And similarly, for the what I call the left side, for the bar operators. You see here, this is lambda bosonic, it stands between 0 and 1. When it's 0, this is a scalar operator. When it's 1, it has transverse spin minus 1/2, which is exactly the spin of the minus component of the fermion. While the plus 1 become the plus derivative of the scalar. Okay. And the match go for the full 4 towers operators between the two. Okay. Tell me if we're going too fast.
So to understand it correctly, you just said that there are no fermionic, there can't be any fermionic insertions in the Wilson line from the mu dx mu. Is that what you said?
If you start with just the Wilson line, there is no operator in the adjoint that you can end on the line and would be relevant or marginal. And to be precise. We will see we'll do something similar but different in the next slide.
Okay.
We will deform the Wilson line. Okay. Because here naively you say there is only one operator, right? But in the bosonic theory we found 2. The alpha equal to 1 and the alpha equal to -1. We see that the standard Wilson line is the dual of the bosonic operator, the stable one, with alpha equal to 1.
Okay.
But we should find another one. If they are dual to each other, we should find another operator that is the dual of the one with alpha equal to -1. But where it is, there is no deformation, no adjoint operator I can add to the Wilson line in the fermionic theory.
Sorry,
So
just,
this is
just to make sure I understand. So, in the case of scalar, did you consider critical boson, or it was just a scalar, a regular boson?
the critical one, the conformal theory.
Sorry, so there.
There are two theories that one obtained from the other by this double trace deformation going to the
Right.
IR.
Right.
But if you're just considering the expectation value of this mesonic line operator, the double trace deformation only contributed to order 1 over n. So at least in order, they don't feel this law. This law will only enter when I talk about the correlation function between two such mesonic line operators.
I see. But your point is that because these are dual to each other, I should be able to find out some analog of alpha in the fermionic theory also.
Yes. Yes. Okay. This is what we expect. So this is was really puzzling what's going on. And a hint comes from, let's look what happened for the spectrum of boundary operators in the alpha equal to -1 operators. So the simplest mesonic line operator was just to put the scalar and the conjugate scalar at the two endpoints on the line. And to see what we should do in the fermionic theory, we take the bosonic coupling to the maximal value to 1, which is dual to looking at the free fermionic theory. And so this is what I said here, at lambda bosonic equal to 1, the dual fermionic theory should become free. So let's see what are we looking at. But the scalars, remember, and the conjugate scalar, they have their anomalous dimension flipped. So when you take lambda equal to 1, the conformal dimension goes to 0. So we should look for some boundary operator who at 3 level is dimension 0, but still spin plus or minus 1/2. This looked really strange to start with. Let me jump to the answer, and this is backed up by all-loop computation. Turn out that we can condense the fundamental fermion in the exponent in the fermionic theory. So here we add to the exponent a fundamental fermion with spin -1/2, and the conjugate fermion with spin +1/2. So if you expand it in the perturbation theory and a number of fermion insertion, this line operator look like some empty part, and then part with fundamental anti-fundamental fermion in between them, a Wilson line. And these points are being integrated. Now, in what I call the empty part, it's not completely empty because these fundamental fields carry transverse spin, which you have to translate to the endpoint of the line. So what enter here is what we call a topological spin connection that transports the spin of the fermion here to the endpoint of the line or to the next conjugate fermion. Now, if you try to construct such a topological spin connection, turn out that you have, even in the free theory, you have to introduce a framing vector. Otherwise, it does not exist. And once you introduce a framing vector, it is unique. So even in the free theory, in order to define such an operator, we have to introduce a framing vector. This is how it, this operator that have part that are filled and part that are empty still carry the same anomalous spin as the Wilson line along the line. We said that this fermion, the endpoint of the line, get anomalous dimension. Therefore, you would naively expect that it wouldn't make sense to integrate it along the line at finite coupling. But if you expand this operator at finite coupling, you also have operator with more and more insertions, and all the divergences, if the coefficient of this fermion is tuned, exactly cancel out. So this is a good conformal line operator, and we match the full spectrum of boundary operators with the one with alpha equal to 1, which is very strange. It has fundamental fermions in the exponent. Yes.
So can you write down the action?
Yes, I try to avoid doing that, but I can jump there.
Just want to see, yeah, how to.
So I can write it like that, where this A tilde is some 2 by 2 matrix. The 2 by 2 matrix for the field, the part of the line with Wilson line and the part of the line without Wilson line. So here the upper component is this, the part with the Wilson line, and the lower component is the empty part with this topological transport, which is written here in terms of the framing vector n. E is a unit vector along the direction of the line. E is x dot over x. And in the off-diagonal term, we have this is a projector to the minus component of phi, or to the plus component of the conjugate phi. Okay. And this part here, when you integrate fermion, you get power divergences. This is a counter term you have to tune to cancel the power divergences that are being generated.
Does psi have the same dimensions as A? Because A is a fermion and A is a boson.
Yes, psi have dimension 1 at the free theory. Yes.
So you actually have a fermion in the action.
Yes. Yes. Which translate between the part with the Wilson line to the part without the Wilson line. This looks super strange, but it's just a fermionic dual of the standard Wilson line in the bosonic theory with the minus in front of the biscalar. Okay.
But can you have can you have naked Grassmann variables in a Wilson line? I mean, shouldn't it be paired with some sort of Grassmann coefficient in order to make it a non-Grassmann number?
It's not a Grassmann variable. I think you are worried that this fermion carry spin, right? When you rotate it around itself, it would pick a minus sign, right? But it's connected here to a topological spin connection that carry the opposite spin.
No, that I understand, but I mean, the fermions, they obey Fermi-Dirac statistics, right?
But this is exactly it. What it means, it is what happens when you rotate them around themselves. Otherwise, if you're talking about the order in order line, this is path order.
I think Amit is
path order.
In the final answer, once you take the 2-2 component, do all psi's appear evenly?
Do all psi appears?
In an even manner. If you go to the next slide,
yes.
You're going to...
Yes, of course. Every psi has to have some psi bar to connect with. When you take the two component, you must do that.
So in the end, in the final answer, there are no naked Grassmann things. It's always paired.
Yes, yes. But these guys that start with a fermion and end with an empty line here, which do appear as the off-diagonal element of this matrix, do appear, and they are good operator by themselves. They would appear once you deform the operator, because one of the good boundary operators is putting there a fermion instead of the empty line that we describe here. The empty line that we describe here is the dual of the scalar, while just putting there a psi is the same as taking, you go back, a longitudinal derivative of that. If I take in a longitudinal derivative of it, I'll put the fermion here. But their number will still be even. They would appear exactly the same number of fermion. For any fermion, there must be an anti-fermion. So this is the match of operator between the bosonic operator with alpha equal to -1 and this what we call condensed fermion operator, the one that has fundamental and anti-fundamental in the exponent. So, for example, the empty part is the dual of the free scalar, and the other bottom operator in the scalar theory, which was the minus derivative of the scalar, is dual to the minus of the fermion. And similarly for the right side, for the left side. Now, it turned out that this operator will they also have a lift to a locally supersymmetric operators in the n equal to 2 theories, which was kind of considered before, because people consider the quiver gauge theories in the n equal to 2 theory, and these operators are obtained by taking the rank of one of the two gauge group in the quiver theory to 1. Okay. then one side become trivial, and one part become with the Wilson line. We can now deform this operator, which gives us a bit intuitive description of this RG flow between the alpha equal to 1 and the alpha equal to -1 operator. If we change a bit the coefficient in front of this fundamental and anti-fundamental fermions in the exponent, we can make the field part expand. Okay, this is a relevant deformation, and we flow to just the Wilson line, which was the dual of the alpha equal to 1 to 1 operator. Okay. But if we take it with the opposite sign, then instead of becoming bigger, they shrink to 0, and what you remain is only with the topological spin transport, but with no Wilson line. This is what I meant by almost trivial line. It still has the spin transport.
This corresponds to the first e to the I a mu x dx mu Wilson line that you talked about, right? I mean, it can't have any.
No, this part here, no. This part here flow to just a topological transport without an operator at all. Just a topological spin transport that you can define once you're given a line and a framing vector.
Yeah, what I'm saying is, if you do the RG flow, since it flows to a pure Wilson line, I mean, without
no Wilson line.
No
here it flows to a pure Wilson line.
Okay.
Here it flows the opposite line. There is no Wilson line at the end of the flow,
Okay.
just a topological spin transport.
Nice.
Okay, just this. I didn't press. Just this part here. I have it in the slide. Sorry. Just this part. Okay? There is no dynamics here, right? And just a parameter.
Yeah.
And this is an explicit function of the path and the framing vector.
Yeah.
Mm-hmm. Okay. So let me talk a bit about the bootstrap. I just have one slide on it, even though this was, I think, the main part of the work.
So,
yes.
So when you deform the fermionic, this funny fermionic line operator with the relevant operator, so that is integrated only on the path that is connected with the black line, or also on the dotted line?
When you deforminate, I meant going to, where is it? Well, here, if you change the coefficient here, instead of being 4 pi over k, you change it a bit, then you generate this law.
I see.
Okay?
Okay.
This is the off-diagonal term that
Right.
separate between the field and the empty part.
Yes. But in terms of this, what is it called? This displacement operator, is there a characterization of the displacement operator in this case?
Yes, of course. So one of the highly non-trivial step is to take this operator, do a deformation, and collect all the contribution. Part of them coming from the gauge field, part of them coming from the fermion, part of them coming from the topological parallel transport, and they nicely combine to exactly the same evolution equation that we had in the bosonic field.
Okay, I see. Thank you.
I kind of jumped on it because the spectrum already matched. Once the spectrum matched, there is a unique operator which is dimension 2 in spin 1. So this is basically fixed for you, also the form of the evolution equation. But this is backed up by an explicit Schwinger-Dyson type derivation. Yeah. Okay. So the main point of the bootstrap is to show that the spectrum of boundary operators plus the evolution equation is sufficient to uniquely determine the expectation value of this mesonic line operator. Okay. So once we match these, we automatically also match the expectation value around arbitrary smooth path. So the way we show that, we start from a straight line, and then expand it in the deformation away from it, so smooth deformation. So this is a sort of 1D conformal perturbation theory where your deformation parameter is dimension 1.
So by expectation value, you mean the line would get dressed or something by the rest of the by the interactions in the theory or the deformations? What do you mean? What would happen when you take expectation values of the mesonic line operators? What difference would it do to the original line operators? Would they get dressed or something in some way?
Deformation here, I mean, deform away from a straight line. So we start from a straight line. If we pick the framing vector to be trivial, then it's some scheme-dependent coefficient or our choice normalization divided by the difference to the power to the dimension of the scalars. Let's say if we put them as scalars at the endpoint, and now we deform away from a straight line to some other smooth shape.
Yeah.
Okay.
No.
So this is the deformation.
I'm concerned with the expectation values. What do you expectation value with respect to what? With the action, right? With the
expectation value of this line. We want to compute the expectation value of this line operator now.
Yeah.
Not of a straight line, but some arbitrary smooth line. Okay, that can have some non-trivial shape. We want to understand the dependence on the shape of the line when we deform the line away from being straight.
Yeah, no, I'm concerned with when you're talking about the expectation value, what do you weight the various lines by? I mean, expectation value means that you have to weight the lines by various weighting factors and then take the then take the average. So I was just
matter Chern-Simons action. The matter just ordinary expectation value of this operator.
Yeah. So that's what I'm saying. I mean, you just
yes, of course. The Chern-Simons plus the coupled to the matter, coupled to the boson or the fermion.
Yeah. So that's what I'm saying. So that would mean that the line, the various operators on the line, they would, or rather the trajectory, the world line would get dressed, right? Dressed by loop insertions and things of that kind, right?
The whole expectation value get correction at every order in perturbation theory.
Yeah.
Yes. Okay. So, but what we did here, the idea is to do something completely non-perturbative. Okay? Giving you an exact operator equation, which tells you what happened when you deform the line, and the exact spectrum. And now you try to use it to compute. Okay? So we started from a straight line. In every order in the deformation, we include all the relevant and marginal bulk operator weighted by the corresponding powers of the deformation. And then, of course, you have to pick a regularization scheme because you get divergences and contour terms that you have to cancel. And then we enforce that the line stay conformal also after you deform it with the appropriate spectrum of boundary operator, satisfying, of course, the evolution equation. But this was not enough to fix the coefficient of all the operators. We have to demand also that other than linear deformation around any path, not necessarily a straight one, the evolution equation is satisfied. And this second condition was enough to fix all the coefficients systematically. For example, then we use it to bootstrap the two-point function of the displacement operator. Okay? Just in terms of the dimensions of the given of the boundary operators, and we find this nice relation. Note that this two-point function of the displacement operator, this lambda, has the property that at the value of delta or 2 minus delta, it is invariant. Okay? 2 is the dimension of the displacement operator, and delta is the dimension of the operator on the boundary. We can pick it to be any one of the 4 operators here at the bottom of these towers. And they are related to each other by delta to 2 minus delta, because when you combine 2 of them, you make the displacement operator, which is dimension 2. Okay? So you see, a priori, this function had to have this property. And this is also backed up by an explicit all-loop computation in a specific regularization scheme. You get wave function normalization factors that are scheme dependent, but in this combination, all the scheme dependence exactly cancel out and you reproduce this function. And again, the same thing you get if instead of starting with a straight line and putting two of these, you start with a circle line and do two deformation. You get it again at some trivial factor times the same function. Let me end with future direction. So here we prove that the expectation value of these bosonic line operators are the same in the bosonic and fermionic theory. To complete the duality between the theory, you have also to show that all the connected, at large n, the connected correlation function between these line operators are also the same in the bosonic and the fermionic theory. And then we expect that the spectrum of the same information that we talked about before, the spectrum of boundary operator and the evolution equation would be needed. And the only new information we have to add to it is the spectrum of single trace operator. So this is where the difference between the quasi-boson and quasi-fermion theory enter only in one number. What is the dimension of J0? Is it equal to 1 or 2? This is the only bootstrap information that have to be added here in order to bootstrap the correlation function. And this is something we are doing now. But again, the punchline is that this information is enough to fix the correlation function. And because this information already matched between the two, they will have the same correlation function, and therefore everything follows from that. Note that for the expectation value of this bosonic line operator, we have shown that it's the same, but we didn't compute it. We only computed it to few order in perturbation theory. It would be nice to find what is this conformal invariant function of the path explicitly. And I think it's something we should be able to do. And let me finish with our original motivation. We wanted to derive the holographic dual of these theories, which is expected to be a parity break-in version of Vasilev higher spin theory. We have some explicit ideas of how this should work. This is where we started, actually. Shiraz, if you remember, this is something we discussed once when we visited Chern, which is why we started to work on this.
I remember, yes.
So, thank you.
Okay, thank you very much, Amit, for a wonderful talk. Let's all unmute and yeah, we have had quite a few questions during the talk, but I'm sure Amit won't mind having a few more.
One question I have, which is a bit different from this talk, but since you consider mesonic operators, I mean, in a gauge theory, you also have baryonic operators, which have in higher dimensions a very important role. Do you have any thoughts on that?
Here we focused on the large n limit. So in the large n limit, this would be a very heavy operator, dimension of order n. So we didn't thought about this because it was mainly focused on the planar limit.
Right. No, but I mean, in the large n limit, baryons are described in terms of the chiral model in 3+1 dimensions. In QCD, I'm talking about. I mean, there is an understanding of all that, right? I was wondering about whether you have some thoughts on the baryons are degrees of freedom here. I mean,
Yes. So we haven't looked on baryon operators. It's a bit related to some work on offer also that studied the spectrum. But I think if I'm focusing on the planar limit, it can play a bit the role of a non-dynamical boundary condition for this operator. You can have such line operator ending, I guess, on such a baryon if you take out one of the fundamental and place the line instead of it. And this can be a nice thing to look at. But it will not be sort of dynamical, it will just play some boundary conditions. So, right, so this dimension is infinite in the planar.
yes.
Sorry, one more question. in solving these theories at large n, it turned out to be as easy to solve the massive theories as the conformal field theories. So I was wondering whether you could extend your calculations of the Wilson lines to a mass deformation of these theories. There, even the straight Wilson line would be an interesting quantity. It would presumably interpolate between pure Wilson line, just Wilson line and pure Yang-Mills theory at very long distances, to what you have here at short distances. And that interpolation sounds interesting to me. Would that be?
I agree.
Would that be easy to study? Yeah.
I would expect there's a similar techniques should apply there, and I agree completely. It definitely sounds interesting. We haven't looked at that.
Okay.
Maybe something in that flavor to add. If you don't pick alpha to be -1 or 1, you don't have RG flow on the bulk, but you still have RG flow on the line. And interestingly, we were able to match even the flow at alpha not equal to 1 at the technical level in the same scheme between the fermionic and the bosonic.
Amit, one question. So this bootstrap part that you mentioned at the end is a bit fast, but can I think of this as taking a circular Wilson line and having 4 operators inserted on it and then analyzing the usual constraints of crossing and unitarity on that? Is that what you mean by the bootstrap?
No, the bootstrap that I talked about was starting with straight line.
Okay.
And doing the deformation of it. So for the simplest case, let's start with the straight Wilson line and just do a small translation of it. So nothing should change. But then I can re-express this as insertion of the displacement operator integrated or 2 displacement operator integrated.
Mm-hmm.
And the fact that it doesn't change give you constraints that fix the coefficient of when you try to write this operator in terms of trivial line plus operator inserted on the line. And we have a complete classification for the operators you can insert on the line. Just have to fix the coefficients.
Okay. Does this also tell you about the OP coefficients of these operators?
Yeah, this is a bit what I was referring to here. So for example, here when you compute the 2-point function of 2 such mesonic line operator, we have two channels, what we call the open and the close. One where they are closing like that and one where they are closing like that. In one side, you exchange all the single trace operators. When we know the spectrum, in the other channel, this is the line operators, the boundary operators we talked about.
Right. But sorry, but if I consider these adjoint operators that you would insert on insert in the bulk of the line, so their spectrum is also corrected in the same way as with this.
Yes, it follows directly from the spectrum of boundary operators.
Right.
The boundary
because of the
factorization. Yes.
Because of the factorization. Yeah. Okay. Yeah. Thank you. Sorry, just one question to complete. So finally, this spectrum of operators then is basically that of the free theory, but with shifted dimensions, right?
Yeah, not all of them are shifted in the same way. Half of them are shifting up, half of them are shifting down. You can think about it.
Right. Okay. Thank you.
Yeah. So in your analysis, did higher spin play any role at all?
No.
So
no, because we just considered the expectation value of this line operator.
That's right.
It starts playing a role here when you compute the correlation function of this. In the closed channel, we exchange the single trace operators and their dimension enter. So this is the only place where it enters. And here also the double trace deformation that takes you from the quasi-Bodel to quasi-fermion theory would be important, and it will enter through the dimension of J0. This is the only bootstrap information you have to add to distinguish between the two.
I see. Just to make sure, in a free theory, if I remember correctly, I might be, if I consider a operator which is phi x, phi y, then if I expand, I think I will get all the higher spin operators. They will.
Right.
So in your case, would you get Chern-Simons corrected higher spin operators, or?
We are not changing the operator content of the theory. We are just, instead of studying the local operator, we are studying these mesonic line operators who by themselves is overlap with the single trace, but not only with the single trace, but also with all the multi-trace operators. Okay. To think about it as some condensed operator that have overlap with all the local operators in the theory, whether they are single or multi-trace.
But
the idea is to study, yes.
But in the large n limit, it would be principally the single trace.
No.
No, I thought it would require pair creation of the fermions to make multi-trace.
So yes. When you, for example, when you consider already the 3-point function of such mesonic line operators, the double trace would contribute at leading order.
Really?
Okay. Yes. But the nice thing, a bit is that you don't have to now bootstrap something. In addition, you get it for free. It's given by some integrated thing of the original ones.
Oh, sorry. You're talking about the double trace in the action.
No, I'm talking about the double traced local operators.
I see. So you're saying you cannot expand at large n. This, let's say a straight Winsel 9, you cannot accurately expand it at large n in terms of only single trace operators.
No, it has all the multi-traces.
Okay.
I have a question.
Yes.
When you consider the expectation value of these two Wilson lines, the connected expectation value of these two Wilson lines, you're saying that it will amount to is inserting certain operators in the middle, in the junction between the. Is that what you're saying?
You can decompose it as overlap of this mesonic line operator with a single trace local operators times propagation of the single trace spectrum times the opposite overlap. This is one of the two channels of the composition of this correlator.
In general, one would expect that, I mean, suppose you have these Wilson lines, right? You have these A's sprinkled over all over the Wilson lines. So one would expect that the A's on one line would join with the A's on the other with the propagator when you take the expectation value, right?
When you take the disconnected correlation function, you have contribution where A on one line is connected to an A on another line.
Yeah.
But such contribution will come also with this, let's say, fundamental here connected to the anti-fundamental here.
Yeah, that is true. But in general, I mean, if you take the non-perturbative limit, then these would become dense and form a sort of, if you take the Hooft double line notation implications, they would form a sort of sheet between the two Wilson lines.
Yes.
So you can directly talk in terms of a theory on sheets when computing the expectation value. I don't know whether that would make any difference or have any advantages to seeing it in this point of view. I'm just suggesting.
This doesn't have, I think, I don't think this is useful for computing the correlator. This is more connected to the holographic dual.
Holographic dual would definitely have something to do with that.
Yes.
Yeah.
The point is that the sheet wants to break down. The moment that you deform it a bit, it breaks down. Okay, it's factorized. Any small deformation, make it factorized.
You have a question, Shiraz?
Yeah, sorry, I'm sorry to keep you so long. I mean, just one quick. Is the reason that this does not expand, that this Wilson line is not a single trace operator, is it because there's this alpha phi bar phi upstairs?
Yes.
Without it would have been, right?
Yes.
Okay, now I understand. Okay, yeah, thank you.
But for the case of fermions, then there is no such thing, right?
But he described this very elaborate construction where there's the analog of this.
So the reason is the same. Okay.
In connections. Okay, if no more questions, let's thank Amit again for a wonderful talk. Very good.
Thank you.
Yeah. Fantastic talk, Amit, and fantastic work. Just fascinating.
Yeah. Thank you, Chiral.